Well, hello guys, welcome back to all of you. And today we have a very important theorem, that is the Jordan-Holder theorem. The statement of theorem, first of all, see the first part: every finite group having at least two element has a composition series. And the second statement is any two composition series of a finite group G are equivalent. It means this theorem we have a two part. In the first part, we have to prove if we have a group and that having at least two element, there must be a composition series. Okay, and in the second statement, we will prove if a group having finite and there exist two composition series, they must be equivalent. It means a group having only a single composition series, if the other exists, that must be equivalent to the existing one. So let's start this theorem, and here we will start first of all the first part of this theorem, that we will take a finite group and that having two element, and we will prove the composition series will exist for that group. Let's start. So guys, first of all, I have taken a group that is G, and the group having order n, which I have taken here. So the group having order n, and first of all we will take that n is equal to 2, because it is given to us that a group having order at least two element is there. So if n is equal to 2, so it means there exist two element in this group. So the one is will be identity and the other will be a single element. So in that case, the only composition series will exist, that is G is equal to G naught and containing G1, that is equal to E. It means if the element is 1, so how we can make another composition series? Okay. So that's why the G1 is a normal subgroup of G naught, and G naught by G1 must be simple. So trivially we can say that this composition series will exist for this group if the order is 2. That's clear, and the theorem is proved. That is the result of this theorem. Okay, now the next thing what we have to do. So if what will happen if the order of a group is greater than 2? So here I'm taken, so result is true for if n is equal to 2. Now we will prove this result for n is greater than 2. So in order to prove this result, first of all we will assume, by induction hypothesis we assume that the result holds for all the finite group having order less than the order of G. So it means we will take all the groups having order less than that group G, there must be a composition series. Okay, so that is our supposition. So it means the group which having order less than the group order of group G, there must be a composition series exist for them. So here I have taken that n is equal to 2. So now the two cases will arise. The case number first, if G is simple, what will happen if G is simple, and what will happen if G is not simple? So there are two cases, the case number 1 and the case number 2. So in the case number 1, if G is simple, then it means there, the simple group definition, that there is no normal subgroup exist for that group G. So it means if G is simple, so it means there is no normal subgroup. So again you can say that the composition series will becomes like that: G naught containing G1, that is equal to E, because we have no normal subgroup there is. So G is G naught and G1 is equal to C. It means the containing identity, that will becomes the normal subgroup for G. And so we can say that G1 is a normal subgroup of G, and G naught by G1, that will become G by E, because G naught is equal to G and E1 is equal to identity. So it will become G, and we have taken G is simple. So you can say that G is simple. So the quotient group, the factor group is simple now, and the composition series is hold. That is equation number 2 is a composition series for a group G. The theorem is again true. But what will happen if the case second, that if G is not simple? If G is not simple, then what will happen? So here we have taken G is not simple in the case number second. See guys, if G is not simple, it means there exists a normal subgroup for G, and we have taken that is N. So N is a normal subgroup of a G. Okay, so if N is a normal subgroup of G, so I can say that G is finite. So there exists a finitely many proper normal subgroup of G containing N. The point is that if G is not simple, so there must be a normal subgroup. So it could be possible that other than this, there exists any other normal subgroup. So we can say that the finitely many proper normal subgroup will exist in G which containing N. Okay, so this N will be contained by any other finitely many proper normal subgroups. So but I'm taken here that is M. So M is that normal subgroup which will contain N. Okay, so M will be the one such a normal subgroup having largest number of elements. That is also we will let here, we suppose this thing. So M will be that normal subgroup which contained N. And I'm saying that this is the such a having largest number. So I can say that the M is a maximal normal subgroup of G. Am I right? Because we have taken a largest number of element. So M is maximal and M is containing what? M is containing N. So we have one result, we have one theorem. We know that a subgroup H of a G is a maximal normal subgroup of G if and only if G by H is simple. So this theorem we have done in our BSc, that if H is maximal, so G by H is simple. So we have M is maximal. We have taken M is maximal, so our GM by M is simple. Okay, so G by M is simple, and M is what? M is a maximal normal subgroup which containing N, and N is a one normal subgroup of a G here. Now what is the role of M? See guys. Now see, you can see the M is maximal normal subgroup, it means M will contain in G and M is a normal subgroup of G. Both things will happen. And order of M must be less than order of G, because M is a maximal normal subgroup of G. So this order will be less than order of G. And we assume this thing by the induction hypothesis. The theorem will proved, the result will hold for all the groups which having order less than order of G. So M having order less than C, it means there exists a composition series for M that will I've taken M is equal to M naught containing in M1, M2, M3, MC. That is equation number 3 I have taken. This is composition series for what? This is composition series for M. Clear? And the two things will happen because this is composition series, so all Mi plus 1 normal subgroup of Mi and all Mi by Mi plus 1 are simple. Two things will happen. Okay, that is equation number 3 and equation number 4. Now see, now consider the series. Now you know that series M is M naught, M this we have taken in equation number 3, and we know that M is containing, but M is containing in G naught, that G naught is equal to G, because M is containing in, as we are saying, M is containing in G actually, because M is a normal subgroup of G. So is this equation is a composition series, but we claim that this equation number 5 is a composition series for G. We will prove, we will claim this is a composition series for G, and our theorem will proved. So from M to MR, it is a composition series, no problem. But problem is here. Is the things will happen? Yes, of course we proved that G by M is a normal subgroup of G and G by M will be simple. We proved this thing in the last part. Yes, here. I think here. Yes, G by M is simple and M is a normal subgroup. We know this thing. M is a normal subgroup. So this part is hold, so we can write a statement like in this series we have only the one factor group which is extra than series, because this series is composition series and this factor group is extra, that is G by M, and we know that G by M is a simple. That is equation number from 4th, and the other factor group is also simple. So M is a normal subgroup of G. So the theorem is proved. The first part of the theorem is proved now, that equation number 5 is a composition series for group G. So the theorem was what? If a group having order at least 2, so there must be a composition series. So we have proved that this theorem, that there is a composition series, and the equation number 5 becomes a composition series for group G. So the first part of this theorem is proved now. Now we have to prove the second part of this theorem, that if any two composition series will exist for a finite group G, they are equivalent to each other. Okay, so how we will prove this theorem? So see guys, first of all, I'm taking the part A. In this part, we shall prove this result by induction on order of G. Okay, so first of all, I'm taking order of G is equal to 1. If what will happen if the order of G is equal to 1, what means the only one element exists for G, it means that element must be identity. Okay, so it means there is nothing to prove because the only identity is there. So how we can construct a two composition series? Yeah? There is no other element for G. So the theorem is proved. Okay, guys. Secondly, what will happen if the order of G is equal to 2? Order of G is equal to 2. It means there exists the one another element extra than identity. Okay, so in that case the series will becomes like that. Already we have done that G naught G1, that is E. It's a trivially composition series because G1 is normal subgroup of G and G naught, like if one element, there is only one element. So how we can construct a two composition series? Because the one element will exist in one composition series, and if we are constructing the another composition series, that is again you have one element, so both will be equivalent. So that's why the result will hold, the result will true, my dear. Okay, So if order is 1, the result is true. If order is 2, the result is true. So what will happen if order is more than 2? If we are taken here, the order of G is greater than 2. Order of G is greater than 2. So guys, let order of G is greater than 2. Now again we will suppose the all the groups which having order less than G, is the theorem is true for that. The result is true for that. Theorem is proved. Like we have taken by the deduction hypothesis, let us assume that the result is hold for all the groups having order less than G. So guys, now as I have order of G is greater than 2, so that could be 3, 4, 5, whatever. But I'm taking here like the two composition series will exist for G, because we have to prove the two composition series if exist they are equivalent. So I have taken two composition series, that is one is for I have taken as a subgroup, that is G1, G2, G3, G up to Gk, and one is for H0, H1, H2, H2 up to HL. Okay, one is going for K and one is we reached for L. So that is equation number 2 and equation number 3. Now our target that we have, we will prove that equation number 2 and equation number 3 both are equivalent, like the both the series, both the composition series are equivalent to each other. So if these two composition series, so we have two cases arise now. What will happen if the first element of this, because we have proved that like G1 is equal to H1, G2 is equal to H2, all are equal, then we can say that the all both composition series are equivalent. Am I right? So we will start this theorem. Let's case number first. What will happen if H1 is equal to G1, and what will happen if H1 is not equal to G1? So the first case arises if both the first element of the both the series are equal. So as if the both elements are equal, so in that case you can say that G1 is equal to H1. So H1 is a subgroup of G. H1 is subgroup of G. So order of H1 is less than order of G. So it means the theorem hold. This result is hold for H1, because we have taken this one. By this result, I'm using that statement. All the groups having order less than order of G will the result will hold. And what is the result? The result is that if the two composition series exist and both are equivalent. Well, so as the order of H1 is less than order of G, so we can take the two composition series will exist for H1 and both are equivalent. Okay, so we have taken the two composition series will exist for H1. The one is we start from H1, G2, G2, whatever up to Gk, and the other is H1. This is. It means uh, in what we have taken in only it will happens in the case if G1 is equal to H1. If G1 or H1 equal and the composition series exists for H1, so this thing we have construct from equation number 2 and 3 as the equation number 2 and 3, that is you can see here that H1 is here and G1 is here. It means the composition series I can replace this H1 as here. So you can see the H1 is here, so the composition series for H1 is this thing, and the composition series for H1 is this. So it means that the other remaining elements both will be equivalent. Okay, the other subgroups are equivalent. It means the both the composition series are equivalent to each other. That is start from here and at end will here. Okay, so this is only happens if G1 is equal to H1. So order of H1 is less than order of G. So by induction of hypothesis, the composition series are equivalent. So it means K minus 1 is equal to L minus 1 and K is equal to L. So it means the both like Gk and HL both are equal. It means K and L also equal. So but some students can also say that why we have written here K minus 1 and L minus 1. We can directly write out K is equal to L. But guys, where we are doing the advanced abstract algebra and we are in MSc mathematics, so this is algebra, so you can't directly say like that. Okay, induction hypothesis. What is the case of induction hypothesis? We already proved, first of all we can prove that for K, and then we reach to the K plus 1. So as same that we now you say that the K is equal to L, so both the composition series are equivalent. But guys, the one vector group is rect, and the one factor group of 4 and 5 are isomorphic. So all the 2 and 3 are factor group which are additional than the 4 and 5. So G naught by G1 is isomorphic to H naught by H1. So you can say that the equation number 2 and 3 are equivalent. So what will happen actually? See, here the series is start from H1 and this is T series from, these are equivalent, no problem. But the problem is this H1 is this series is start from here, and we have to prove the series from here. Okay, So these are equivalent from this again, the part, these are equivalent, but we have some additional factor group that will becomes G by G1, G by H1, these kind of factor groups. And we have proved here that the factor group G naught by G1 is isomorphic to H naught by H1, because guys, G1 is equal to H1 and G naught is equal to H naught. We know this thing. G naught is equal to H naught and G1 is equal to H1. We have taken here in this part. So that's why both are isomorphic. So you can say that hence the composition series 2 and 3 are equivalent to each other. So this was your first part of this theorem. Sorry, second part. And in second part, we have taken the case number first. So we have proved that in the case number first, if G1 is equal to H1, so theorem is proved. Now we will take the case number second. What will happen if G1 is not equal to H1? So in that case, we will prove this theorem if G1 and K1 are not equal. So in that case, we can say that there is exist one K, okay, that will be equal to G1 intersection H1, yani that will be equal to intersection of both of them. Both are not equal, but the K is equal to intersection of both of them. It means K will include in G1 and K also include in G1 H1, as both are in G and both are in G. So we know that as G1 is a normal subgroup of G and H1 is a normal subgroup of G. So we will prove that G1 and H1 is a normal subgroup of G. First of all, we know that G1 and H1 is subgroup of G. As we have done the theorem in BSc, HK is equal to KH, then HK is a normal subgroup of G. I hope so everybody remember that theorem. So by that, G1, H1 will be subgroup of G. And we will claim that H1 and G1 is a normal subgroup of G. And also we will prove that G1 H1 is not other than G, like G1 H1 is equal to G. We will also prove this thing. So let's see guys, first of all, first thing we have to prove that G1 H1 is a normal subgroup of G. So here I will take a one element from G1 H1, that is X, and one element from G, that is Y. So we will prove at the end that is Y inverse X Y. And how we can prove, let's see. So guys, if X belongs to G1 H1, so X is look like that, G1 into H1. G1 belongs to G1 and H1 belongs to capital H1. So X look like that, the multiplication of two element, okay, and Y that will be from G, so Y will be Y. So here you can write out Y inverse XY, which we have to prove in order to make our normal subgroup. So Y inverse XY is equal to what? Y inverse, as it is, X is G1 and H1. So X G1 H1 Y is equal to Y inverse G1 Y. So I insert here Y into Y inverse, nothing else, in G1 and H1 as Y into Y inverse and H1 Y. So here I can use the bracket, Y inverse G1 Y is separate and Y inverse H1 Y is separate. You know, G1 is a normal subgroup of G, and we have taken the as element that is G1 from G1, capital G1. So you can write out Y inverse G1 Y, that will belongs to G1, because G1 is a normal subgroup of G. So this thing will belongs to G1, and if H1 is a normal subgroup of G, so this thing will belongs to H1. Okay, so this complete element belongs to G1 and this complete element belongs to H1, and both are in multiplication. So it means that the complete element will belongs to G1 and H1. So it means Y inverse XY is belonging to G1 H1. This is belonging to G1 H1. Clear? So guys, you prove that G1 H1 is a normal subgroup of G. So G1 is H1 is a normal subgroup of G. We prove the first thing. Now see, now I will prove that G1 H1 is not other than G, that is equal to G. Why it is so? See, if G1 is not equal to H1, both are not equal and both are normal subgroup. So it means G1 and into H1 is not equal to G1 and G1 into H1 is not equal to H1. If both are not equal, so if you will multiplying the one by H1 and other things, like you are multiplying both side by H1. So it is H1 and H1 into H1 becomes again H1. Okay, so both will not equal. Now see guys, we have the two maximal normal subgroup, one is G1 and one is H1, according to this composition series, equation number 2 and equation number 3. You can see here, this series start from G1, this series start from H1, and after that we have G0 that is equal to G, and after that we have H0 that is equal to G. Now what you have proved? You prove that G1 H1 is not equal to this one and not is equal to this one. It means what? And that is a normal subgroup. The first normal subgroup is start from G1 and this first normal subgroup start from H1, and we are saying that we have any other normal subgroup which name is G1 H1. So where is it? Where is it? So G1 is a proper subgroup of G1H1. So it means G1 contained in this. Am I right? G1 will contain in this, and similarly H1 is proper subgroup of this thing. So H1 contained in this. So it means what is G1H1 actually? G1H1 actually is equal to G, because we have a series like we have H1 properly contained in H2, and then properly contained in H3, and as so on. Like, and what is there? What this is H naught, and what is there? There is G actually, guys. That is equal to G. So it means if H1 is containing in H1 is here using H1 is containing in this, it means there is existing a one at G1 and H1 in which containing the H1 is containing in this thing, and that must be equal to G. Okay, clear? In the place of H naught, I can write out at G1 H1. It means this G1 H1 is the maximal normal subgroup. Okay, and this is equal to G actually. So by equation number 6 we prove that G1 and H1 both are equal to G. Okay, what is the benefit of this? Now see, so as we have taken that K is equal to intersection of G1 and H1, and that is finite, and we know that every finite group having a composition series, so it means there exists a composition series for K now. So I can take a composition series for K, that is K naught, K1, K2 up to Km. Okay, now it's a composition series for K. Now see guys, I can consider a two composition series. I can consider two composition series, one for G, that is G naught G, this is K up to K2, K3 up to Km. Second for G is equal to H naught H1, and after that is K. Why it is so? Because K is what is K? See guys, K is a properly containing in what? Properly containing in G1, and K is properly containing in H1. Properly containing in H1. So by this source, you can see K is properly containing in G1. Here you can see K is properly containing in G1. K is properly containing in H1. And after that, I can use this complete composition series as same, like in the above result, in the second result, same. I had written here. So G is equal to G naught and G. Now these both series will help us to prove this theorem. Okay, now you can see the composition series is both are composition series and both are equivalent, because both are in the terms of K and both are reaching up to M, K, M, both are, everything is same. But the point is that the only we will check it out before that K, before K what will happens. So we claim that equation number 8 and equation number 9 are composition series for G. So how they will becomes a composition series? Now see guys, we will use this the concept of fundamental theorem to prove this. It is sufficient to prove that H1 by K and H1 by K, G1 by K and H1 K by are simple. Why we have to prove this thing? Because only I already told you the things only we have to prove, only we have to see only is this one, right? This one, H1 by G and G1 and G. Like before this, after this we have the two composition series, both are equivalent. Before that we will see there are two factor groups. The one factor group is G1 by K and other factor group is H1 by K. So if both are simple, so our the equation number 8 and 9 will becomes a composition series and both will be equivalent. So guys, here we will use the second fundamental theorem, and the second fundamental theorem, so if we have a two subgroups and normal subgroups, so we have G1 H1 by H1 is isomorphic to G1 by G1 intersection H1. So here you know G1 H1 is equal to G and G1 intersection is equal to K. So here you can replace the value of this one is G as this one is a K. Both will be isomorphic, and you know this thing that G by H1 is a simple from equation number 3. As we have taken equation number 3, equation number 2 and equation number 3, we have taken the two composition series. We have to prove both are equivalent, but two are composition series. So equation number 3 is a composition series. It means G by H1, where will it becomes this factor group definitely simple. So if this is simple, so you can say that G1 by K is simple. Similarly, now you can replace H1 as G1, like G1 here you can use and H1 is here you can use. In that again, this replace as G and this replace as K. Here you know that G by G1 is also simple, equation number 2, because earlier we taken the two composition series. One is in the form of G, G1, G2, G, and one is in the form of K, K1, K2, K as equation number 2 and 3. Equation number 2, that is for the equation number that will be as a composition series of G as in the form of G1, G2, G3. So this is simple. So it means H1 K by simple. So the both factor groups G1 by K and H1 by K both are simple. So it means so all the factor groups of 8 and 9 are equations are simple. That will helps us to make the proof of this theorem, because 8 and 9 the composition series is series for G. That is our proof. Okay, because also we know that the first factor group of 8 is isomorphic to the second factor group of 9, and the second factor group of 8 is isomorphic to the first factor group of 9. So it means the equation number 8 and 9 are isomorphic to each other. Each and everything is isomorphic to each other. Each and everything is equal actually. Okay guys, so now, someone can think that we have to prove this theorem for equation number 2 and 3, as we have taken the two composition series as equation number 2 and 3, one in the form of G and one in the form of H. So it means we have to prove that the equation number 2 and equation number 3 will become a composition series and both are equivalent. So guys, in that case, you can also write out also by the case number first. Case number first, as H1 and G1 are equal. And here also the case number of n, first as h1 and g1 are equal. In that case, you can say that if both are equal, so it means equation number 2 and 8 are equivalent. Okay, in that case equation number 2 and 8 are equivalent. See guys, what is equation number 8? Equation number 8 is this one. Start from g naught, g1, k up to this one. Okay, and what is equation number 2? Equation number 2 is also in the form of a g, that is g1, g2, g3, g up to gk. So as both are equivalent, okay, because that two equations are, if the both are equivalent, in that case you can say that easily that is reaching to the m and this is star to k. So it means k is equal to, in that case you can say that what is k is equal to, here the start element from k naught to km, but the two elements are extra. The one is this one and one is this one. It means in this complete series we have totally m plus 2 element. So I can say that if the both series are equivalent, so k is equal to m plus 2. Similarly, if we will compare equation number 3 and 9, so l is equal to m plus 2. So you can see that k is equal to l. Both k and l are equal. So equation number 2 and 3 will become equivalent to each other. Okay guys, so this was the theorem, the complete theorem. So again, just take a recap for the complete theorem. So guys, Jordan-Holder theorem, we have the two cases. One is finite group having at least two elements of the composition series, and second, if we have a composition series, both will be equivalent. Two composition series, both will be equivalent. So firstly, you have taken an if order is 2, so nothing to prove. Then you will take, if order is greater than 2, you will take the all the group having order is less than 2 having a composition series. So in that case, two cases will arise. One is G is simple. If G is simple, nothing to prove because there is a non-normal subgroup. And in the second if case 2, if G is not simple, in that case there will be exist a normal subgroup. One you will give a name n, and you will take a m, that is a maximal normal subgroup, and by the help of maximal normal subgroup you will say G by m is simple. So if m is a normal subgroup and order of m is less than G, so there exists a composition series for m. You will say that this is a composition series for m. So this series, you can extend this series for G, and after that you will claim that this series becomes a composition series for G, and that result is proved. In the second case, you will take two composition series, guys, because first of all you will take if n is equal to 1, nothing to prove. If n is equal to 2, nothing to prove. So if you will take n is equal to greater than 2, in that case you will take a two composition series, and one is in the form of G and one is in the form of L, and we will prove that both are equivalent to each other. So what you will take, so guys, there are two cases arise. One, if G1 is equal to H1, and if G1 is not equal to H1. If G1 is equal to H1, so the first elements are equal. So in that case, the both series will equivalent, nothing to prove. And in the second, you will take if G1 is not equal to H1. So here you have to take care of one thing. You have to consider one K, which is equal to the intersection of this. Firstly, you will prove that G1 and H1 is a normal subgroup of G here. After that, you will prove that G1 is equal to G, like G1 is equal to G. So now you have to prove, you will take as K is equal to intersection and K is finite, so there is a composition series for K, and you will replace this composition series in the equation number 2 and equation number 3. So both G series and H series will convert in the form of K. Okay, and you can see here K, after this there is a composition series and both are equivalent, but you have to prove that before this, so there will be a two factor group. One is known as G1 by K and one is known as H1 by K. So to prove these factor groups are also simple. So you will use the second fundamental theorem, G1 H1 by H1, and isomorphic to this. Okay, so G1 H1 is equal to G. You can write out this also. You can write out, and you will say that both are simple, like both G1 H by K and H1 K both are simple. If the factor groups are simple, so equation number 8 and 9 cell becomes a composition series for C. So this was the theorem, complete theorem of Jordan-Holder theorem. So I hope so that this will be helpful for you guys, and I will upload the notes, complete notes for this theorem. So I hope that you will support me, and keep support. Please share to your friends as much you can support me. Thank you so much guys for watching this. Keep watch, keep support.